Hi guys. Or evening, morning, evening, or afternoon, depending on when you're watching. So this will be day 4 in physics, and this is going to be we're going to be taking a look at Coulomb's law today. So let's open our blackboard up. And what I want to look at today, we kind of looked at Coulomb's law yesterday at the very end of class, and today we're going to be looking at Coulomb's law in a little bit more detail. We'll be look at one-dimensional questions and a couple of maybe two-dimensional questions as well. And that'll be the area that we study for in terms of Coulomb's law. And then we'll move into electric fields next and how we form electric fields. Okay, so we'll wait for the board and we'll set our outline up here. Okay, so we're going to do a couple outlines, a couple of things in our outline today. First, get it all set up here. All right, so this will be day 4, unit 3. And we're looking at, obviously we're in the electrical field, so we're going to be looking at Coulomb's law. Should have a capital there, sorry. And what we're going to look at in Coulomb's law is we're going to look at look at some examples today. So our basic idea is to look at examples in one dimension and in 2 dimensions. Okay, so when we're doing the 2D stuff, we're going to have to pull out vectors again, okay, just like we always do. Okay, so yesterday we did an example. So just to remind everybody what Coulomb's law looks like again. Okay, so if we're looking at Coulomb's law, the equations for the force between 2 point charges. Remember, it's not large charged objects, it's just like point charged objects. We have the force equaling K, which is the constant that we use, Coulomb's constant, Q1 and Q2. The 2 charges, and then it's divided by r squared, which is the distance between the objects. Okay, just hang on, guys. I'm going to shut the door here, and I'll be right back. Okay, so that's what we're dealing with. Now, we remember that Coulomb's law also has the constant, the Coulomb's constant is equal to 9.0 times 10 to the 9th newtons meters squared over Coulomb squared. Okay, now that's the constant. Now the elementary charge, we're going to talk about the elementary charge later when we talk about electric fields a little bit more. Okay, and the first one we did was we did an example of one-dimensional. Okay, when you have the charges along the same line. So let's kind of let's do another example like that real quickly, and then we will get into the 2-dimensional ones next. Okay, so a little bit different than yesterday. Let's say a balloon that has 5.6 microcoulombs. Okay, so microcoulombs times 10 to the negative 6, remember? Of positive charge on it. Okay. Balloon is 48 centimeters away from let's say negative 4.4 microcoulomb microcoulomb charged rod. what force does the rod exert on the balloon if the rod is to the left of the balloon? Question mark. Okay, so we're going to have a situation, and we should also say assume that they're point charges or small charges. So if we have a rod here like that looks like this, okay, we'll just make this into a little bit skinnier. So if we draw our positive rod here, and this is positive, and we've got our balloon here, and it's sorry, this is negative. I got it backwards here. Pardon me, guys. It's a negative rod. I got a negative in front of it. Right, -4. So that's negative, and this is positive. And the balloon and the rod are 48 centimeters away, or if we like, 0.48 meters, because we're going to have to change it into meters to use the Coulomb formula. So the force of the rod on the balloon, we'll go R on B, is going to equal, now if this is positive and this is negative, they're going to attract each other. So the rod is going to pull the balloon towards, so it's going to be towards the left. Okay? So this is going to be K times the charge on the balloon times the charge on the rod over the distance squared. Okay, so if we plug our numbers in, a K is 9.0 times 10 to the 9 Newton meters squared over Coulomb squared times 4.4 negative it is, but that doesn't really matter in this. It just tells us which way the force is going to go. If it was the same charges, the force would be going the opposite way, repulsion. Okay, 4.4 microcoulombs, so that's times 10 to the -6 coulombs, times, I'm running out of space on my edge here, I should have put it closer, times 5.6 times 10 to the -6 coulombs, all divided by 0.48 meters squared. Okay, so if we do our math here, move that up so we can see it a little better. Okay, and I'll maybe work a little bit over. So if we're doing the force now towards it, so if we multiply all these together, our calculator, we get on top 0.22176. Okay, because we got coulombs canceling out, that squared coulombs there, and then the meters canceling out, squared meters here, and we're going to get over 0.448 squared, which I didn't work that one out. Let me work that one out. So that is 2304. So this is going to give us, what do we get here? Clear that up, 0.22176 divided by 0.2304. So we get 0.9625. To two significant figures, 0.96 newtons. Okay, and this is going to be towards the rod, which in our case is left because it's attraction, because of the negative and positive charges attracting each other. Okay, if they were the same charge, it would be the opposite direction because it's going to have a repulsion force. Okay, now we did an example of a single step, or not single step, pardon me, collinear force. But what if we had an example that was not a collinear force, but it had a force of with some objects at a angle to each other? Okay? Okay, we're going to look at that. Or what if we had to find the distance between? Or what if we had to find one of the charges? Okay, it doesn't always work out that you have to find out just the force here. So let's do an example where we have to calculate one of the other values given the force is given to us already. Okay, so let's do one like that, and then we'll work on the two-dimensional one as well. Okay, so this is an example of given the force, finding one of the other variables. Quantities, we'll say. Okay, so let's do finding distance. Let's say a negative 5.9 microcoulomb force or charge is some distance from a negative, so they're both 4.8 microcoulomb charge. A 5 microcoulomb charge is some distance from a negative 4.8 microcoulomb object, we'll say. Period. The force of repulsion is measured to be 1.0 newtons. Find the distance between the two objects. Period. So in this case, we're going to be finding R. So if we look at our result, we have a force given to us, 1.0 newtons. K is always the same, 9.0 times 10 to the 9 Newton meters squared over Coulomb squared. We know that charge of the first object, we'll call it 1, was negative 5.9 times 10 to the negative 6 coulombs, because we need it in coulombs. Charge of the second object was negative 4.8 times 10 to the negative 6 coulombs. Okay, and the R value is our unknown. So if we plug it in to our formula, okay, we can try to solve for R first if we want, or we can plug our numbers in and then solve for R. It doesn't really matter how you do it, as long as you're solving for R. So I'm going to plug our numbers in first. So we got 1.0 newtons equaling 9.0 times 10 to the 9 Newton meters squared Coulomb squared times the first charge, negative 5.9 times 10 to the 6, negative 6 coulombs, times the second charge, negative 4.8 there, times 10 to the negative 6 coulombs, all divided by R squared. Okay, so what we're going to do is get rid of these coulombs. are going to cancel out each other, and then these forces are going to cancel each other, and we're going to get meters squared, and when we root it, we're going to get square meters. So if we leave it like that, we go 1.0 equals, and if we multiply all these numbers together, we get 0.25488 on our calculator over r squared. And that's the product of these three numbers, hopefully. Okay, then we have to solve for r. So we have to multiply by r squared on both sides. So 1.0 r squared equals this number. So simply put, anything times 1, you divide by 1 is going to be the same thing. So we have to take the square root on both sides. So square root it. And this is going to be in meters because we have square meters left. And then when we root it, it's going to be left in meters. So then we get, what do we get there about? About 0.5. Or 50 centimeters. So they're about 50 centimeters apart in that case. Okay, so that's finding other variables. Now the only other one I want to do today is an example of doing a two-dimensional one. So we'll do a two-dimensional one, and that'll probably take us to the end of the period or close to it anyway. When we see that. So let me just pause and let me find a good example here to look at. Hey, let's look at a two-dimensional example here now. So I looked up one. So let's say that we have this picture. Okay, so say we have a sphere here. Let's actually draw a straight dashed line here first. Oh, we don't want an arrowhead. Just a straight dashed line. So let's say we have a straight line like that, and let's say that we have another straight line like that that are 90 degrees to each other. Yeah. Okay. So let's say that they're in the center part, let's say that we have 3 spheres, or 3 point charges, if you like. So one's there, one's here, and one is here. Okay, and let's label them A for the center point here. This is sphere A, this is sphere B, and this one we'll call C. Okay, so we have these 3 charges, and okay, I'll give you the sizes here. So let's say that charge A is 6 microcoulombs plus 6.0 microcoulombs. So that's a micro symbol. It's like a fancy U. Okay, charge B, I'm just getting it off my example here, is negative 3.0 microcoulombs. Okay, and then charge C, we're going to say is, what is it here? Positive 1.5 microcoulombs. Okay, and then there's some distances in between each of these spheres. So the distance from A to B, okay, so let's see. A to B is, where are we here? 4 centimeters. Okay, and then this distance from A to C, let's say that is 2 centimeters because it looks about half from here to there. Okay, notice that we have 2 positive charges and 1 negative charges. And the question is, what is the net force on sphere A? Okay, so we've got a force. Okay, so we've got a force along this dotted line that we drew here. We'll put it in blue. Let's actually use a little arrow here. So we have, now is it going, there's attraction. So B is going to pull A towards it. So it's not going to go that way. It's going to go the other way, right? So let me just, so B is the opposite charge. So it's going to attract it here. So B is going to pull it towards itself. Okay. Now these are the similar charges. So this is going to push A away. So C is going to have a charge like that. Okay. So we'll label those 2 blue charges. So the force of B on A, we're going to label. Let's make it a little bit skinnier here. This one's going to be the force of B on A. Okay, because they're opposite charges, so they're obviously it's going to be attracted to the opposite charge. Okay, and this is going to be the force of C on A. Okay, I wouldn't recommend it.
You wouldn't recommend it?
Well, you can if you want, but how much do you flop around?
Not that much. I only flopped around once and I fell off a bunk bed for it.
Okay, well, it's not that far, I guess. Okay, so I just have a couple guys in here that are getting ready for their lock-in thing today. Okay, so that's the 2 forces. So what we have to do is we have to take these 2 forces and then do a vector diagram after that. Okay, so the first thing is step 1 is to calculate. Let's do force B on A. And then calculate C on A. Okay, and we know the directions are based on our diagram. So the force that we're going to get is going to be going to the right in our diagram. That's going to equal, okay, Q1, Q2 over R squared, and Q1, A on B, so this one will be A, I guess, and this one will be B. Okay, so if we plug in our numbers, 9.0 times 10 to the 9. Okay, I'm going to leave the units out just to save some space, which I shouldn't do, but I'm going to. The charge of this one is 6 microcoulombs. 6.0 times 10 to the negative 6 coulombs. This one here is negative 3.0 times 10 to the negative 6 coulombs. And then we're going to divide that by this squared in meters. So 4 centimeters, 4.0 centimeters equals 0.01 meters. Okay, so this is 0.04, pardon me, meters squared. Okay, so that's going to be our force of B on A. So let's take our calculators out and crunch the numbers. Okay, 9 exponent, okay, oops, that's wrong, 9, okay, scientific notation, 9 times 6, scientific notation, -6, that's weird, eh, times 3, scientific notation, -6, and it looks like that on my calculator. Okay, and I get 81 over 500, or 0.162. To newtons, and that's going to be towards, okay, B is going to track, so B is going to pull it to the left, or to the right. So that's why we don't bother with the signs in there, we just use our diagram. Okay, now we're going to do step 2. Okay, so step 2 is to calculate the other force, the vector force of that. Force of C on A. Okay, so C on A is going to pull it upwards, right? Okay, so if we do that, we got to put in our variables. I'm not going to rewrite them like this. I'm just going to write the equation. That's going to be 9.0 times 10 to the 9. Okay, A is going to be the same charge, 6.0 times 10 to the -6. B or C is going to be 1.5 times 10 to the -6. Okay, keep in mind that C is pushing on A and getting, because they're repulsing each other. Okay, all over 2 centimeters as in meters is 0.02 squared. Okay, wait a minute. I think I forgot to put the square underneath here. Sorry, guys. Right? I only did the top there. I think I forgot. This is 0.162 over, and I forgot to do the r squared, didn't I? So let's go back and do that. So 0.04 squared, that's going to make it a little bit different for sure. There, that's better. This is 0.0016. Okay. My mistake. Good thing I caught her there. Okay, so obviously I did the top one, but I forgot to do the bottom one. Okay, so then I go 0.162 divided by 0.0016.
There we go.
So I get 101
Way too long.
0.25 newtons. There we go. Okay, so that's our force. Okay, sorry about that. I hope you guys were watching and were going, what's he doing? What's he doing? Okay, but we caught it there. So we have to be careful about that. So if we do this one, okay, let's do the top. 9, scientific notation 9 times 6, scientific notation -6 times 1.5, scientific notation -6. So that gives me 0.081. But this time I'm going to remember to do this 0.02 squared. Obviously that's 0.004. 0.02 squared is 0.0004. 3 zeros. There. So then if I do that, dividing 0.081 divided by 0.0004, end up getting 202.5 newtons. Okay, now that we have both of our forces, we then have to do step 3. We have to draw a vector diagram. One is an up force and one is a left force. So this one we ended up We'll fix this answer down here as being 101.25. To the right, this one is 202.5 up. Okay, then step 3 is to get the magnitude of the force by using Pythagorean theorem. Okay, so let's move that up a little bit. So step 3, okay, we're going to use Pythagorean theorem. We're going to sum the vectors Okay, we're going to sum those vectors perpendicularly. Okay, we're going to use Pythagorean theorem or right triangle. Okay, so let's draw our diagram. Okay, we've got 101 to the right, 0.25. So we'll start here. And then we got 202, so like that. So then therefore we're going to get a solution that is right here. Okay, and we have to be careful about the angle because we need angles as well. Okay, and we could also go up and then over, so then there's two ways to do it, just like any vector. So, sorry guys. Let's label it. Okay, this was 101.25 newtons. This was 202.5 newtons. And this is going to be R, capital R. So R squared equals 101.25 squared plus 202.5 squared. Okay, we're doing Pythagorean theorem. So we take out 101.25 squared plus 202.5 squared, and we get a total of 51,257.8. Okay, and then we square root it. To get 226 newtons. Okay, now that gives us the force, but we don't have a direction. So step 4 is to find the direction. How far up from right do we have to go? Okay. Now we don't have north, south, and east and west, so we're just going to use right and up. Okay. So when we state this, we go, okay, let's find the tan theta. Step 4, get the angle. Okay, that's going to be opposite over adjacent. So that's going to be 2. So inverse tan of 2 equals theta. So we take out our thing, go second function tan to get the inverse tan of 2. We get 63.4, we'll say 63. So that 63 degrees gives us above the x-axis. If we can say that this is going to be 226 newtons right 60 degrees up, or 63 degrees above. I guess we should put right first. Okay, so I'm going to write it like this. We're going to go right. Okay, since we don't have any directions, we're going to go right. and then we're going to go 63 degrees upwards. So that means when we're thinking about the direction, we go right, and then we go 63 degrees upwards to get to that. Okay, obviously you could have went this way first, and then over. Okay, so you could have went upwards, and then whatever that would be, 90 minus 63, 27 degrees to the right. And that would have been fine too. And that's how you get a two-dimensional force between three objects that would be perpendicular to each other like that. Do we do any other ones? I think we're going to probably stick with only perpendicular ones in this electrical force one. Okay. Okay, I'm just going to pause here and see if there's anything else we need to take a look at here for this, and then I'll be right back. Okay, so basically that should close out our our point charge electrostatic area. So just to summarize, and then we're going to get into electric fields next day. So just to summarize, you should know the laws of electric charge. This is our first area that we did. Okay, so like charges attract, like charges repel, opposite charges attract, and sometimes highly charged objects attract neutral objects. Okay, you should know charging by contact. Okay, or induction. Okay. You should be able to do a charging by induction problem as well with that, or contact problem, like we did as an example. You should know what a conductor is, or an insulator. Okay. Okay, and then we should know Coulomb's law in one dimension. One dimension or two dimensions. Okay, so those are the basic four things that we looked at in the first section. Okay, the one thing you can try if you have some electrostatics equipment, you might want to do a little test on, charging objects, see which objects attract which other objects. Here in Vanguard, we've got a whole bunch of stuff, balloons, different kinds of rods, glass rods, ebonite rods. So you can check out and see if you can get some charges that work there. And we're going to stop there for today. That's about 40 minutes. Okay, so next day, we'll start looking at the electric field. How do you get electric fields? Okay, so that's our topic for next day. So we'll see you then.